Good afternoon, everyone. Welcome to Innovation Insights for April. This is the 12th edition of Innovation Insights. It turns out we started this last May, still during the pandemic, and it's great to have presented now roughly 30 plus entities, including our core partners, small and medium enterprises and large enterprises. Today we have a great lineup going forward, but first thing I want to do is just show the IACMI mission and vision statement. Some of you may have seen this before, some of you haven't, but the vision is improving everyday lives through the power of composites. Our mission is to convene, connect, and catalyze the composites community to accelerate advanced composites design, manufacturing, technical, and workforce solutions to enable a cleaner and more sustainable, more secure, and more competitive U.S. economy. We organize around these main themes of convene, connect, and catalyze through various methods. So we have a number of ways of doing that, including this webinar, our members meetings, and other activities, with folks to, bring people together, then connect them to each other, and then to catalyze innovation in this industry. Just a little bit about our summer members meeting. A reminder that will be this summer, June 28th through 30th in Salt Lake City. There will be working group meetings, high-level speakers, great networking reception at the Utah Museum of Natural History. So if you're a fan of rocks and geology, or of dinosaurs and mastodons, or Native American culture, you will be in for a treat at that museum. So the registration is open at iacmi.org. It is free to IACMI members. There is a cost if you're a non-member to attend. So, go there and get signed up. More details there. Innovation Insights, all of our previous versions are on the IACMI website. So if you go to the IACMI website and go over to events, there's a tab for Innovation Insights, and they're all recorded. So you can actually, go through, look at each one, the information, decide if you want to go back and see something that you might have missed. So from a schedule standpoint, this is the April edition. There will be one next month, Monday, May 16th, making sure we're separating from JEC by a week. And then we won't have one in June because of our members meeting in Salt Lake. And then we will shortly announce the remainder of 2022. So that being said, we're going to get started with today's. Our first speaker is Adam Halsband of Forward Engineering North America. Adam is the managing director of that entity, and I'm going to turn it over to him right now. I will ask that you put your any questions or comments in either the chat or the Q&A panel, and we will get to those as we go along. So,
thanks so much, Dale. My audio okay, and can you see my screen?
Everything looks good.
Super, super. Well, thanks so much, Dale, Kim, and all the IACMI team for the opportunity to participate in the Innovations Insights webinar. This super exciting program. I've enjoyed a number of them in the series so far, and looking forward to sharing how Forward Engineering is working to accelerate the development of high voltage battery enclosures. Real quick, Forward Engineering, for those that don't know who we are, I'm Adam Halsband, Managing Director of Forward Engineering North America, based here in Royal Oak, Michigan. My colleagues are based at the headquarters in Munich, Germany, and my colleagues in Nagoya, Japan, at Forward Engineering Japan. We are an engineering services company. We help to accelerate the development of composite-intensive mixed material solutions, leveraging our material and production-based engineering technology. So anybody interested in learning more about how we're doing these things, please let me know. But without further ado, let's jump into the topic at hand. So battery enclosures. Battery enclosures are the most complex subsystem within the vehicle today. Now, we could argue that point, but from our experience and the projects and programs we're fortunate to be working on, the battery enclosures as we move onto an electrified age are one of, if not the most complex subsystems within the battery electric vehicle, within the vehicle. From structural crash, crush, EMC, moisture, liquid intrusion, thermal management. There's a very broad range of requirements, and not the least of which is thermal runaway. When we think about requirements for these high voltage battery enclosures, it really is a mix of regulatory requirements and OEM technical requirements. So forward engineering, we spend an enormous amount of time on understanding how to translate those global regulatory requirements and the variety or mix of OE requirements into relevant requirements at a subsystem material level. So we're working with folks up and down the value chain to understand how to translate those requirements to material level requirements, system level requirements. For today's Innovations Insights, we're going to focus on thermal runaway of the multitude of different functional requirements and mechanical requirements. And we're fortunate to work with a number of different IACMI members. And I should have shouted out earlier, we're very proud to be an IACMI member, but working with a number of different IACMI members and others on advancing different solution sets for the multitude of functional requirements. But today we're going to focus on thermal runaway. Historically, and by historically, I mean prior to 2019, 2020, when you would talk to folks about the most stringent regulatory technical requirement driving battery enclosure development material selection, they would point to the bonfire test. So GBT, China standards, European standards, the ECER 100 shown there, have a requirement for external fire on the battery enclosure and the enclosure being able to withstand that event that's defined within those standards. At the end of throughout 2019, China was developing new standards in response to what they were seeing in the field. Others were watching and observing what's going on with respect to the development of those standards, and that brought on the release of the GB 38031 in 2020 with a new set of requirements, which was safe vehicle egress. So basically, an alarm must be alerted and provide the occupants of the vehicles 5 minutes, a minimum of 5 minutes time to exit the vehicle without affecting the occupants. With respect to understanding how those regulatory requirements translate to subsystem requirements and material level requirements, what were the standards, what were the requirements? And we were being asked by our industry partners, our clients and partners, how do we understand, how do we translate those system level, pack level, vehicle level requirements down to a material level requirement. And we were fortunate to be working with a particular OEM, and I'll share with you in a moment, who was pushing to understand this. And we worked with different material suppliers and subsystems suppliers around the globe to understand what tests are out there. And many of you may be familiar with flame testing, the traditional UL94 type testing, and that evolved into torch testing. So amping up the Q factor, the flow factor, how much energy you are putting into these samples, and measuring backside temperature, frontside temperature, and does the sample withstand that? The reality is a thermal runaway in a battery enclosure is much more complex than just temperature. And folks had identified that, recognized that, and developed a torch and media or a pyrotechnic test. And there's different ways that you can include abrasive media or ablative forces on the samples when you're testing to screen materials for applicability in battery enclosures. The reality is it's not just temperature and ablative forces, it's temperature, pressure, and ablative forces that are required that the samples, these materials must endure in order to have a realistic screening of materials for applicability at a vehicle level or at a pack level. So as I alluded to a moment ago, we were fortunate working with the materials engineering team at Hyundai Kia, They were asking these questions of what are the materials engineering team at Hatchie were asking the question, what are representative testing standards? How do we develop or identify the most representative screening methodology at a sample plaque level to represent system level performance? Out of that was born the box thermal runaway test, which has been captured by the Underwriters Laboratory folks. We worked with, collaborated with the Underwriters Laboratory folks to capture that test as UL 2596. So what that test is, and I'm going through rather quickly, I apologize, with the limited time available, want to share as much as we can about this exciting development. And that was actually published in January, the UL 2596, but essentially, what we're doing is we're utilizing a 5x5 array of lithium ion cells, 18650 cells, and we're initiating thermal runaway of those cells and imparting that energy on the sample. So when you look at the image on your screen and you see that brown panel, that is the sample under test, typically around 200 by 200 by an appropriate thickness sample. The nominal thickness is typically around 2 millimeters. And what we're doing is using resistive heaters, and I'll show you some detailed images. We're using resistive heaters to gradually and gently bring the temperature of those cells up to approaching the point at which they go into thermal runaway on their own. And that's part of the magic, is to gradually and smoothly initiate thermal runaway. And then once that thermal runaway begins, all 25 cells go into thermal runaway. And again, back to the point of its temperature, ablative forces, and pressure. And we control the pressure within that enclosure utilizing a fixed plate orifice. So that green object, that cylinder that you see in the center of the images there, that's a fixed plate orifice, a fixed hole in the box. The only place gases, energy can exit that enclosure are through that orifice. And based on a known amount of energy inside that enclosure and that restriction, we're able to manage a target temperature range. As you'll see in the data results, a 16 millimeter orifice runs you about 250 kPa plus or minus. And because again, we have got 100% state of charge cells in there, 25 cells of known chemistry, and they're going to deliver a certain amount of energy when they're run into thermal runaway. We repeat that test 3 times. We evaluate temperature, pressure, and monitor with high-def video, which I'll show you, to observe how the panels perform, how these materials perform. Get into a little more details here real quick. So here's a close-up of that orifice. You can see the cutaway in the upper left of that image, showing you the focus on the pressure control orifice. You can see the lithium ion cell, that 18650 cell in the background. In the image to the right there, you can see some wire, which is used to contain those cells or hold those cells as we're dropping them in, and you'll see that in another image. The items over to the right there are the, I think I can use my cursor. So here we have pressure transducers, thermocouple, and we're measuring pressure and temperature inside the enclosure, temperature on top of the sample, and that's some close up there. Here's a dive inside the enclosure. You can see that array of cells. These 2 center cells are wrapped with a thermal resistive heater. Power lines run to that, which gradually at X degrees per minute bring the temperature up of those cells and initiate thermal runaway. And here's the the fun stuff. This is not what you want to see. So in the event that the sample does not endure. Now, having said that, not what you want to see, the reality is we want materials to perform good enough. So sometimes when you're running the samples, you're going to push the limits of what those samples can do. And that's what you're seeing here is a sample material which did not withstand the pressure, the energy that was imparted on that sample. On the sample on the right, you can see a material that did withstand that sample or that energy imparted upon it. So I'll real quick jump over here and show you what it looks like real time. that would be an example of a sample panel that yielded, that did not endure the event. Now, let me quickly show you an example of a sample that did endure that event. And this is, of course, the fun stuff you want to see, where we have a composite sample that has endured the incredible forces imparted upon it by a thermal runaway event, and gives us good confidence that when we scale this up and when we apply this material at a scale level, that it will be able to endure that event. Again, being sensitive to time, we can see these curves here, and this is the type of data that's generated from the reports. We have temperatures that the samples are being exposed to, 1,000, 1,200 degrees, that nominal pressure that's being imparted on that sample inside that enclosure, a low of nominally 200 kPa up to almost 400 kPa with the nominal 240 kPa. Topside temperature, this green line showing you the temperatures on top of the sample. And we love to go through in detail and review with the folks that run these tests, the results. It gives us great confidence in what the materials can do at a pack level. So I very quickly went through in a really fun topic, and welcome any questions, Dale. I'm sure there will be, whether online or offline. Pass back to you.
Yeah, thanks, Adam. It's it's really interesting, and we'll have people, if they want to, get the questions in, and then if you can keep asking your questions while we move on to the next presenter, and then Adam, if you'll look for those in the chat or the Q&A, then you can answer those and make sure you answer to everyone. But one of the things I have is, what do you think makes a good material for this? I mean, is it the ablative characteristics? Is it stiffness? You have to obviously balance a lot of things in order to make this work. Yeah,
you hit it right on the head, Dale. It really is like so many other designs that you do. It's about a balance. A super stiff material isn't necessarily the best material. There's a balance between stiffness and ductility. When you look at that event and these pressure pulses, there are materials where folks initially early on, it's like, oh, well, I've got this really, really strong, which was a proxy for stiff material, and that pressure pulse actually cracked the material. Once you crack the material, well, that's not good. So it's a combination of properties. And whenever we're running these tests, we sit down with folks who are going to run these tests and say, okay, what have you got? What are these materials? How can we combine them in such a way to deliver that performance? So it's a mix of temperature, pressure, and ablative resistance.
Okay, question that came in the Q&A is the composite sample, does it necessarily need to be a flame retardant grade?
Short answer would be, to pass this test, we've seen materials that people otherwise would not have classified as flame retardant be able to endure the test. Having said that, there is flame, and those materials do often ignite. And that's one of the characteristics we look for. So I don't want to say that it has to be classified as an FST, FR type material in order to perform well. Often there's some level of FST, FR attributes that are in those materials.
Can you actually go to Northbrook now and get this test done? Or who does this test?
Right, so whether you contact us or contact UL, Katie Hayes is the key point of contact at UL, and we can share the UL contacts to chat with them. And scheduling, as you can imagine, a lot of people interested in this, so we're scheduling weeks and months out in advance to get this test. Today, it's being run at the Northbrook laboratories. That's where we're running those tests. Okay, good. Now we'll need to move on. There are a couple of questions I see popping in the chat and in the Q&A. So if you'd go answer those for folks, we'd appreciate it. Thank you, Adam. Yeah, obviously a very timely topic and very, very important to understand as we go forward. Okay, thanks. So we're going to move on to our second presenters, set of presenters, tag team here.
Billy Wood is the program manager for braided fabrics for A&P Technology. He's joined by Brandon Strohminger, who is an applications engineer for A&P Technologies. Gentlemen, take it away.
Thank you, Dale, and thank you, the IACMI team, for allowing us the opportunity to present A&P's products and technologies today. We'll burn through these the slide decks pretty quick here, so we welcome any and all comments and questions either offline or afterwards. So what is braiding? Just really at a high level, it's going to create fiber continuity in the form of a sock or a sleeving at a 2x2 twill architecture. Sort of nominally, we'd like to orient everything at plus or minus 45, but the real advantage to braid is that we can orient those angles and kind of work with the customer to optimize performance anywhere from plus or minus 15 all the way up to about plus or minus 80. Braid has the ability to be both biaxial, again, that plus or minus 15 to plus or minus 80, or triaxial, so incorporating a 0-degree yarn or axis of orientation as well. We are located in Cincinnati, Ohio. We are a small business with about 200,000 square feet of manufacturing space under roof. And we welcome you guys. If you're ever in the Cincinnati area or you want to learn more about braid, kind of get a hands-on, some hands-on use or applications with it, to come visit us at our tech center here in Cincinnati. So what about A&P separates us from other converters or specifically braiders out there in the world? It's that we design and build all of our equipment in-house. We're able to very quickly scale up and build equipment, as evidenced by the orange or this burnt orange circle here. This is a 700 carrier, which is about 2.5x larger than anything you're going to see on the commercial market. But we have braiders that are even larger than that, capping out currently at 864. We have plans to build a 1,000 carrier braider, and then some longer term plans to go even higher than that. So what can you do with this with a large machine size? You can do two things. You can make a very large sock. We've modeled cases where we could braid something the diameter of a 737 fuselage. We are actively braiding UAM, sort of tactical UAV sized fuselages currently. Or you can make something using very fine yarns, so a thin cell wall. So think rocket nozzles and such. So having this ability not only to build the world's largest braiders, but lots of braid sizes in between really allows a lot of flexibility for folks like Brandon to work with the customer base or people interested in braided composites in general to really right size and drive cost out of applications. Three primary product lines, as you can imagine. The first one, the most common one, would be sleevings. But then from there, we can slit the sleeving open, lay it flat to create a fabric. And impart some of those virtues that we talked about with the braid angle optimization into a broad good, which then can be pre-pregged or preformed. So utilizing or marrying the rotational speed of the braider with the take up to create something that's really just kind of a drop and shoot. Again, the focus on optimizing performance while reducing touch time and labor. Sleevings, where would these be used? Prosthetics, propellers. We're seeing, along with battery box enclosures, a high interest in these types of applications. Why? Because the sleeving's going to have fiber continuity from root to tip. That helps impact performance, fatigue life, etc. Ease of layup and repeatability, right? If we do our job right and we provide you a sleeving at the correct diameter with the correct number of ends, every time that you lay this up on your tool, it's going to give you the same exact layup, improving first part quality. Here's a great application for sleevings. So this is actually a hybrid sleeving. It's both a biax and a triax. It's triaxial here at the bottom region. biaxial at the upper region that's outside of the proud portion of the tool here. So just kind of laying that down, we're going to integrate, well, at least in this case, we introduced a drawstring yarn. We pull on that or activate that to create the downward flange, and then we can pad out the outer flange, introduce a couple noodles, and then a capture sort of surface ply, and voila, you have a window frame. So, and as I mentioned on the previous slide, all of these braid angle changes are repeatable. And as you can see here, the layup was simple and efficient. Because we can predict the braid angle, something that can be managed, measured, and designed against. We've done, it's worth noting, we're not going to touch on it a lot in this short presentation, but a lot of work with thermoplastic recently, where we used our kiso architecture, which we'll touch on in a few slides. So a 0 ± 60 architecture using slit tape thermoplastic unidirectional prepreg conforms quite well into this similar type application. Braided fabrics. 0, it's neat that this is actually the only product that's not braided, but what we're able to do is to get a very wide and very high fiber aerial weight unidirectional material in a sort of a columnized form or a fabric form that can then be readily infused. So think 800 plus GSM, but still available, but still able to infuse quite readily. I mentioned a few slides before that braid naturally forms at ± 45. We pass that efficiency onto the customer in the form of our Bimax or TX45 fabrics. So if you are cutting on the bias, whether, well, in this case, ± 0.90 on a ± 45, and then kitting and laying it up, I think you'd be better served, using your 0.90 and then feathering in ± 45, or obviously if the design calls for 45 across the board, as in the case with a lot of high aspect ratio parts or something that's torsional design, just go straight to the source, and then off the roll you can have a ± 45 solution, saving upwards of 30% scrap and a significant amount of layup time and management. I mentioned we have 2 different forms. Bimax, it's very straightforward. It can be pre-pregged readily because we do introduce a small amount of glass axial yarns. So it has a high level of conformability, but still able to be sort of managed by hand without it sort of distorting all over the place. If you do need a higher level of drapeability, we do have TX45, which comes on a poly backer. Moving to a tri-axial design, our standard product offering would be kiso, which is 0 ± 60, with equal weights of, in this case, we're showing carbon, but we're fiber agnostic, so supplier and material type. So we braid metallics, organics, ceramics, quartz, glass, aramid, etc. But really here with kiso, the fiber area or the fiber yield in the 0 direction is going to be equal to that in the ± 60 by weight, or by yield, excuse me. The cartoon here is actually courtesy of Boeing. They were using 4 plies of woven, half of which had to be cut and oriented at the ± 45. So already a candidate for Bimax, but really taking that next step in efficiency and going to kiso, they were able to cut a 4-ply stack that's balanced down to a single ply of kiso. So the takeaway here is not that 1 ply of kiso is necessarily stronger than 4 plies of woven. It's the ability for the user to design to strength and minimum thickness. So, and that's essentially what we did here, is that whether it be a single ply, 3 plies, or 53 plies, you're no longer bound to multiples of 4 or 8, of which of those 4 8 plies, half of which have to be cut it and oriented. How does kiso drape, right? So we've done a lot of automotive applications, working with Ford and a number of the OEMs out there, but kiso drapes very well compared to unidirectional, traditional 0.90 woven, and then even some of the quadratic or the quad NCF materials out there. So Drape with a high level of infusibility as well. We would like to say, and this is great and kind of really demonstrates IACMI's ability to put together different industry folks, but kiso was involved in some of the testing that was done at Forward, and we've been working with IDI and a number of the entities out there to show kiso's viability in the battery box enclosure market. So the ability working with folks like Brandon to tailor to meet the strength and stiffness, as well as the flame resistivity requirements. So as noted or sort of demonstrated in the cartoons previous, high rate, the ability to lay down, material very quickly in any orientation, get the roll utilization. We don't have a lot of waste off the edges because everything can be consumed because of the uniform properties in all directions. There's another video showing how the sleevings can be laid up quite efficiently to create a torque box type structure, then overlay kiso for a control surface. So this is courtesy of our friends up the road at Hawthorne Composites here in Ohio. They also take advantage of a noodle. So yeah, they're incorporating sleevings, fabrics, and noodles, really three of the product forms that we highlight here at A&P: sleevings, fabrics, and preforms. Some applications using braid: golf clubs. All of the Callaway golf clubs use a form of kiso. Prosthetics, baseball bats, a lot of board sports. Control surfaces, as we mentioned, this is flying on Boeing aircraft, tactical UAVs. And one thing that we didn't touch on, just kind of trying to focus on high rate industry, but another way that we can be high rate but then also drive cost out would be with preforming. As noted here with the tactical UAV, we do aircraft interiors and thermoplastics, stiffening elements, braided propellers, infrastructure, tooling, and satellite or communication dishes, pipeline repair. And that's really about, well, at least it for the 15 minutes that we were allowed. So would certainly, I'll take some time to walk through the chat and Q&A to answer any questions there. But back over to you, Dale.
Thanks, Billy. Yeah, braiding's a really amazing process. I remember, first being acquainted with it back in my old Fiberite days. We had a textile technology, and did some braiding at a 256 carrier braider, I believe, and did a lot of cool things with that. And of course, I think you guys really busted on the scene with, and I think in aerospace big time when you developed the containment case. Braiding, the Kevlar containment cases for jet engines to protect against blade throw out, and then I think it's good to see you continuing to do a lot more in aerospace. You guys still supply, I presume, the braid for the frames for the 787.
Yep, the 787 actually, correct.
Yeah, infused frames. Yeah. What do you think and I think a lot of people underestimate the power of a 0 ± 60 laminate. We all see think quasi-isotropic as being strictly a 0.90 ± 45, but the 0 − 60 is a really clever way of achieving a balanced laminate with fewer plies, and it's good to see. I think braiding is obviously a perfect way to create that.
Yeah, no, absolutely. So you see the 0 ± 60 architecture in some really weight sensitive applications like solar arrays, but as far as or some satellite space applications, but you're absolutely right. I mean, if you're doing the pi over 4 QI laminate, I think you'd be, and you're looking for cost savings, time savings, moving to the pi over 3 of the 0 plus or minus 60, especially because it's, everything's right there in a single ply, would be very beneficial, I think. And then also, because every ply is going to be the same, you get the added benefit of impact performance in a lower, more consistent CTE. So there's some additional virtues or benefit that go from moving from that more traditional pi over 4 to a pi over 3 stack. Anything you want to add to that, Brandon?
No, that's great. And yeah, one thing I was going to say too is we have done a lot of testing on kiso as well. We get that question all the time. We've got a lot of data with a lot of different resin systems that we're willing to share with people to help build confidence and get people started.
Yeah. Surprised the unidirectional material there, and thought about how do you braid a uni material, but yeah.
Well, and some of our customers want a one-stop shop, right? So they love the braid's conformability, but need localized areas of unidirectional stiffness. So that's where we hop in, and we said, okay, yeah, braid can do that too.
Yeah, and the plus minus 45 obviously is a nice, useful tool for people who use a lot of fabrics and and find themselves with a lot of cutting scrap when they're trying to do a quasi isotropic layup. Have you done some work where you obviously, if you buy a woven fabric, orthogonal woven fabric, and combine it with the plus minus 45 braid, how does that compare against, cutting and sewing, or cutting the woven fabric on a bias? Do you see any drop in mechanical performance, or?
No. I mean, I think the one thing that we would not caution, but the one thing that we typically bring up is that braid is most cost effective at plus or minus, or excuse me, as a 2x2 twill. So 2x2 twill plus or minus 45. If you're already using a 2x2 twill drop-in replacement, you're going to see the same properties. But we have baseline compared our plus or minus 45 to plain weave, and statistically, it is exactly the same. So from all the major properties that we've tested it against, the material is going to come back in pretty much the same population.
Okay. Don't say any specific questions in there. I mean, think there's always novel materials like this, and I mean, I presume you're not limited by fiber type, or even making hybrids.
Yeah, no, we do that quite often, especially the automotive market and infrastructure market's a great it's a great case study for that, where they'll need localized areas of high stiffness where carbon makes sense, but the majority of it needs to be something low cost like glass. So we do that quite often. We'll selectively place carbon where needed if there's going to be some kit cutting, let's say for stringers or hat stiffeners or things like that. So really, we would welcome the opportunity to talk to the designers and say, what do you need? We can kind of put that, take all of these wants and needs and then spit out a number of different solutions where it could be something as simple as a sleeving that you're laying up, or something as elegant as us over braiding material to really drive touch labor out of your application or your process.
Yeah, great. Appreciate it, guys. Folks have any questions specifically for Billy or Brandon, put them in the chat, and they'll answer them as we go forward.
Yes, sounds great. Thank you.
Thank you. Okay. So, given that this is the 12th version of Innovation Insights, thought it'd be a good opportunity for folks who are joining us that may not be fully familiar with IACMI's history, some of the things we've done, how we were created, and what we're about. I would pull together a little bit of a retrospective. So I'm going to share my screen and then talk about that. Try to get this to Kim. Are we seeing the right thing, or are we seeing?
No, it's still not. It's still not showing the duplicate. It's showing your. your whole deck on the left still.
Yeah, I need to get something to close here.
Will it let you just take the slideshow from there?
Yeah, I'm just struggling to get the.
I think one more escape and you'll be there.
Yeah.
Hit the display settings and flip flop it. You're in presentation.
Yeah,
mode.
I was able to see that earlier. Now I'm not able to. Okay.
Worked perfectly during practice, of course.
I know it did. I know it did. So yeah,
There you
it's
go.
not. What's that?
Well, now we see you.
I know. I stopped sharing for the moment. So, but what was happening is I'm not seeing.
If you hit display settings, will it work?
Yeah, that's what I'm trying to get to, but I can't get to it due to the taskbar being in the way.
Oh, because I can see it.
Yeah, I know you can see it. And it worked fine just a while ago. So.
If you'd like, you can send it to me and I can try to run it.
Okay, let's try this again. Let's first, why don't I get it started first and then I'll share it.
There's a hint here that you can drag the Zoom taskbar to the side.
Should have it now.
Okay. Yes.
All right. I don't know what happened. Always works in practice, doesn't it? You know, and I've
Yes,
been
it
doing this a long
does.
time.
All right, you're off.
All right, good. All right. So yeah, I called this a retrospective IACMI's Greatest Hits Volume 1 to look back at from the start of IACMI to where we are today. Sorry if for those of you who may not see your favorite tune in this deck, you know, you can't always do that in a simple collection. So we'll move along. So just like a Greatest Hits CD, you'd have multiple tracks. So, you know, these are the tracks that I'm going to cover today. You know, the path that we took, some creating capabilities, making stuff and remaking stuff, and you'll understand when we get to those sections, some cool science behind it all, and then kind of an outcomes section. So just for perspective, and back in 2013, the Department of Energy issued a request for information around a Composites Institute, issued a funding opportunity announcement in February of 2024. And we formed our team at that point, which included core research partners as well as key industry folks. You know, we were kind of driven by what we were seeing elsewhere in the world in composites, particularly at Fraunhofer, at the National Composite Center in UK, you know, at the kind of capabilities that we saw there and the kind of innovations coming out of those places. And so it was really important for us to say, how can we quickly catch up, you know, and in some cases surpass. We went through the proposal process. We were awarded in January of 2015, so not 2105, but we did launch in the middle of that year. You know, the goal initially was around 2020 and 25 targets. In reducing cost of composites by 25%, particularly carbon fiber composites, reducing the embodied energy in carbon fiber composites by 50%, and increasing the recyclability of all composites by to where 80% of composites could be recycled or demonstrate recyclability 80% level, with further targets to 2025. Had to create a membership models, capabilities, operation models, and then start managing a portfolio of projects. The overall goal at the end is to increase U.S. manufacturing competitiveness. To do that, you really have to attack multiple variables. You have to attack the material side, form factors, waste, how you reuse the materials, how do you lower the cost of them, and so forth. The manufacturing processes themselves, speeding those processes up, making them more reliable, and also how do you deal with recycling and joining. And then design and simulation, rather than add a lot of weight just to have great safety factors. Now, how do we get closer to performance on that with insertion points along the way? You can see some of the leading research universities and national labs that became our partners here, kind of spread a bit across the US, along with some additional regional partners that we added in New York and Washington State as we embarked upon this. Now, IACMI connects to the composites industry in multiple ways. Of course, we're funded by state and federal investors from the Department of Defense, Department of Energy, from various state partners as well, from their economic development entities, various trade associations that we interface with, professional societies. We actually do collaborate and work with international consortia. We share much of the same problems worldwide, and we want to make sure that we're all approaching them in the best way. And then, how we get the word out through our communications partners. And then big component of all this is workforce development, but none of this happens without this, I call it this big sea of industrial members. And almost every member on this list, one time or another, worked on a project with us. So, and again, it just doesn't show everybody, but it shows a lot of the members that did work on projects over these years. So in order to get there, we had to create some capabilities, but we had a good starting point. We had facilities in place at many of our research sites, over 300,000 square feet to start with, over $200 million in replacement value investment, and then went from there. And so 5 years later, we have new world-class capabilities for composite manufacturing in multiple states. And I'll walk through a few of those real quickly. In Tennessee, where we're headquartered, new fibers and composites manufacturing facility. The carbon fiber technology facility already existed, but there's also a new pultrusion line in that facility and some other capabilities. The Joint Institute for Advanced Materials was built in this time frame. And then the third building at the manufacturing demonstration facility, which is pretty impressive, also came about in this time frame. Now, we can't claim credit for creating all of these, but certainly the assets that became available to us to do the work we needed to do became available from there. A week after our first members meeting in 2015, we had a groundbreaking in Indiana. It was literally a cornfield that had been mowed down. And a year later, just over a year later, was the Indiana Manufacturing Institute, which does have injection and compression capabilities. Recently, a large-scale additive manufacturing research laboratory. And then its main focus is around modeling and simulation. So those pieces of equipment are used to validate a lot of the modeling and simulation work. And I'll talk about that a little bit later. In Colorado, we had an empty shed out there that in June of 2016, by roughly 6-7 months later, had a fair amount of equipment in it, in which we were able to build a 9-meter blade, and has since done many other things. In Detroit, in April of 2014, our partners at the Lightweight Metals Institute took over this building in downtown Detroit and Corktown. Many of you may have been there. Full of graffiti, leaking roofs, and so forth. Got it to a stage where we could take over half the building and do some things as well. So you can see here in September 2016, we're digging holes in the floor to put pilings in, and then spent a fair bit of time digging a pit for a very large press, the 4,000-ton press that's there. So today you walk into that, you wouldn't even have known the kind of shape it was in back when it occurred. We've got clean rooms, the big presses, classrooms, pre-preg line, many things there to be able to carry out the work that we want to do. Our partners at the University of Dayton Research Institute had equipment kind of strewn all over Dayton campus buildings did consolidate their labs in the summer of 2017, so into what was formerly the NCR headquarters. And then in 2020, opened the Dayton Composite Center with the globe equipment there and some other pieces of equipment to focus a lot on emerging markets like urban air mobility. So with all this capability, we've got to make stuff. And I'll talk about a few projects. One of the big highlights was the carbon fiber liftgate interpanel with Ford for the Mondeo/Fusion. Dow and Dow-AXA had developed a special molding compound, carbon fiber molding compound that had properties similar to cast aluminum, and that was due to its unique architecture in the platelets. You can see the 4,000-ton press there being used for molding this part. The charge pattern being laid up on the left. Cure cycle of under 3 minutes, which gets you to 100,000 pieces per year. You see some of those inner panels. It was bonded to an aluminum outer panel and tested. The material has Ford specification and is available to any Ford engineer who wishes to specify it on a vehicle for a particular application. Similarly, Volkswagen approaches to develop a lightweight liftgate to replace a steel liftgate on the Atlas. This was went from 10 steel parts to 3 parts in composite. One of those, although you still mold those in only 2 tools, so you have kind of a family mold for the left side there on the outer. Weight reduction of 36%. Initially, this project thought it might need to incorporate some carbon, but it turns out we could do this all with glass materials for the low density outer and a high glass inner. Again, big steel tool molding the panel in the press. You can see a number of outer panels, a very complex inner panel. Geometry was very important there in terms of achieving that stiffness. And this is useful for as Volkswagen continues its electrification. Composites don't have to be a premium product. In this case, their recurring cost study showed that the SMC liftgate was 10% less, or 9% less costly than steel and 37% less costly than aluminum. In the wind area, we did some novel work with taking textile pan carbon fiber, pultruding that for a spark cap, built a 9-meter blade. A lot of small samples, a lot of work in infusion trials, and and then making this 9-meter blade out of helium. Helium is a recyclable thermoplastic. This also had a recycled PET foam core. This led to the development of a 13-meter blade that was built on additively manufactured tooling and then bonded together and prepped for testing. Then the testing was done compared directly to an epoxy equivalent of this same size. So it showed to be fairly even to that, and and as suitable replacement for epoxy after 1 million cycles. 3D printing. Friends at Oak Ridge had been doing a lot of work in this area. You can see that 3D printed wind blade tool on the left. Lots of other components using carbon fiber reinforced thermoplastics and developing a whole range of materials, including bio-based materials. You see the one on the top, which is bamboo reinforced polylactic acid. But some of that early work inspired a lot of other people, like Local Motors, for whom we did several projects leading up to the 3D printed ollie. And then for development of new materials for what you see on the right, which is the Al Davis Memorial Torch at Allegiant Stadium, which is currently the world's largest 3D printed structure. So if you've seen that torch on television during the NFL games, it's all 3D printed structure with aluminum cladding on the outside, or stainless cladding on the outside, sorry. And then finally in this area, couldn't leave without talking about infrastructure. We worked closely with several of our partners at Composites Applications Group and Structural Composites to replace a rural bridge in East Tennessee using a composite, foam-filled composite bridge deck, sandwich structure there that had a road surface on it and came in and dropped in. And one of the unique things about this is that has a school bus driving over every day, big heavy trucks, and it's fully instrumented with sensors that relate, every time something goes over, that signal goes back to the University of Tennessee, where they're able to monitor it, and the pictures taken. So some very large vehicles have driven over that bridge. We see this as a great solution going forward for rural bridges in America. I'm talking about remaking stuff. I'm talking about recycling. You can reduce your waste, but what do you do with the waste that you do have? And there's various levels here, and we've had projects in all of these levels, all the way from repurposing all the way up to recovering fibers from end-of-life parts. So 7 years of innovation in this area, going back to the Composites Recycling Technology Center, working with ACMA, working with a whole host of partners that you see down here. So, and then you see some of the things here, the benches made from recycled prepreg, aerospace prepreg, big wall panels or countertops being made from ground up waste, and reflective surfaces here on using pyrolyzed carbon fiber. And then even down here with the filament using Vartega's recycled carbon fiber in a 3D printing application. We worked with Vartega. Remember the Ford liftgate, that material, any of that scrap material was sent to Vartega for recovering the fiber. It was put into thermoplastic pellets, sent back to Detroit, injection molded into fenders, so it made the complete loop. One of the key things here is when you do use recycled fiber, you can see pretty significant reduction in the amount of embodied energy that's in the fiber, and then consequently the amount of energy that you get in reduction for the finished part, in this case, the injection molded part. So big demonstration there on how to get embodied energy back out and reutilize a very important resource like carbon fiber. All this has included a bunch of cool science. It included, for example, on the liftgate project, flow studies, non-contact measurement of fiber density, certainly crash performance correlation, digital image correlation for that fiber orientation after the molding. You see here the modeling simulation of that platelet prepreg SMC being molded. That informs the static stiffness and, of course, the crash performance of the part. On the liftgate project, we initially thought there might need to be some continuous fibers in there, did a lot of work in co-molding studies, but also did virtual coupon approaches to molding SMC, which was surprisingly consistent and very informative. Also on the liftgate project that we started with, that had to start with a steel design, went all the way through that, and we wound up with a very lightweight, all composite design that met all the requirements. And again, digital image correlation, was used to validate fiber orientation in that part. On the blade project, early material characterization showed that helium glass fiber could compete with epoxy glass fiber, both in static testing as well as fatigue testing. We also, some interesting things there. I talked about the 3D printing of the skin molds, using simulation software for blade infusion, and then a novel technique devised by Vanderbilt University to measure surface temperature and correlate that to degree of cure in the part. So when you can see through the bag, you can measure the surface temperature and then correlate that to degree of cure, so you know when you're done. 3D printing, these a lot of coupons being made. These are basically 1 foot by 3 foot coupons, very deep, and a fixture was made to test those. So this really helped inform locomotors and others about how to design with 3D printed structures with various infill patterns, which was used to help design the ollie. Purdue did a lot of work in developing material cards for 3D printed systems that go into an additive manufacturing workflow. So you can do the process simulation, both from a machine standpoint, material standpoint, and then understand residual stress, the creep, and other performance requirements, similar to any other composite material. Big advance there. And then finally, in this section, non-destructive evaluation is a project done at Michigan State University and sponsored by the American Chemistry Council. Is how can you measure parts in a factory, carbon fiber parts in an automotive factory at 1 a minute? And this was done using air-coupled ultrasonic technology combined with eddy current technology, very novel. They had to actually make their own circuit boards for the transducers to do this. So reports on a lot of this stuff is on our ACMI website. If you go into the projects, you'll see reports. And finally, I'll wrap things up with some outcomes. You know, we obviously been through a pandemic. We continued through that with over 50 projects involving 90 members and $150 million in over of R&D value. Over 150 ACMI members have been active in IACMI. And of our industrial members, over 2/3 of those are small and medium enterprises. So that's a very important role to connect folks together. On our workforce side, a lot of work with doing interns, Composites training participants, which are now back in person as of last week, STEM outreach, and then key statistic about our interns is that 100% of those who graduated have a job offer or in a graduate program. A couple of slides, we did have to go virtual for a couple of meetings, but we're back in person again since last October and again this summer. A couple of things about, you see some of the interns and where they've wound up, but places like Orbital Composites, Northrop Grumman, Volkswagen, and Interim. We created working groups around specific topics and markets. Those were created in October of 2020 and were purely virtual for almost a year. Got to meet in person last October, and we'll meet again this summer in Salt Lake City. So if you've got a particular market interest, these are the working groups you want to be part of. Bunch of ribbon cuttings and startups, and, you know, for putting in a lot of new facilities. Obviously, lots of news made over the years, and I won't spend a lot of time on this, but you know, both from our industry partners as well as our core research partners, continuing their awards that have been won by IACMI outcomes. And then finally, my last slide here is just that, you know, what IACMI is a connected community. These are pictures from various members' meetings or visits to member companies or educational opportunities, things like that. So with that, I will stop sharing, and we have hit pretty much the top of the hour. So as Kim has noted, if you're interested in a working group, contact Kim Budden or myself or anybody else. So I just want to thank all our presenters for today. We've hit the 1 o'clock hour, and you know, I will leave the line open if anybody has some specific questions that we can answer in the chat. Thank you very much. We'll see you next month.
Thanks so much, Dale. Appreciate the opportunity.
Thanks, Adam. Thanks, Billy. Brendan.
Thank you, Dale.
All right. Take care.
I don't see anything else in the Q&A or the chat, so looks like
Okay.
the questions were all answered, so I think we're all set.
Think so. All right.
Thanks.
Thanks, Kim.
Thanks, everybody.
Thanks, everybody. We're going to stop the recording.